Good morning, everyone. My name is Jiang, and I'm from the Stevens Institute of Technology, and my professor is Dr. Wina Meng. And today, my topic is about the mixing kinetics of the ultra-high performance concrete. So before we're talking about that, let me briefly introduce the advantages of the UHPC. So as we all know, it has a very high mechanical strength. The 28 days compressive strength can usually over the 120 megapascal. And the 28 days tensile strength can over the 7 megapascal. And compared with high performance concrete and the conventional concrete, the UHPC have the string hardening behaviors as shown in the attached figures. And due to the superior workability, or we can see the self-consolidation properties, the UHPC generally just require very low construction energies to achieve very high construction quality. And fourthly, UHPC has very good sustainability due to it has a very low life cycle cost and excellent durability. But actually, we still have some challenges in the lab for the large-scale UHPC production. As shown in the figures, sometimes the mixer might be stoppage due to the overload of the mixer engine during the large-scale UHPC production with a normal mixer in the lab. So if the mixer is shut down during the mixing process, it might damage the mixer engine, or the rest of the materials will be dumped. So that's not what we want. For now, the student and the researcher in the lab, we trying to minimize the malfunction possibility. We prefer to use the ice water together with reduce the mixing volume. And here is we reviewed some report from other DOTs. We can see actually the output capacity of the mixture is significantly higher than the allowable volume in order not to damage the mixer. So, but the existing solutions absolutely still have some limitations. The extremely low mixing volume will significantly reduce UHPC production efficiency. And the cost and the construction time for each the UHPC element will be significantly increased. So what is the reason the mixer will be shut down? We can see this figure actually compared with conventional concrete. The peak mixing torque for the UHPC is much higher. And if the peak torque is over the limitation of the mixer, the engine will be shut down. So in this figure, the mixing torque refers the required resistance by the mixer during the mixing process. So the whole mixing process during the mixing torque evolution during the whole mixing process, we define it as a mixing kinetics in this research. So why the UHPC is different with the conventional concrete? It's hard to mix. So before we're talking about this, let me briefly introduce the mixing process for the concrete materials. The mixing process can be generally divided into 5 stages. We can call the wetting, nucleation, consolidation, growth, and homogenizations. In the wetting and the nucleation stages, actually the liquid materials like the water and the water superplasticizer is absorbed into the granulars. And the consolidation and the growth stages will start when the surface of the granulars become wet. So what is the water to wet the surface of the granulars have 2 sources. The first one is the extra water in the mixture design. For example, we have a mixture design with very high water to bind ratio. The second one, the water can be squeezed from the inside of the granulars. Right, but as we all know, due to the extremely low water to bind ratio, so UHPC, the water for UHPC, the water to wet the surface can only from the inside of the granulars. That's lead to the UHPC takes longer time and harder to be homogenization. So in this research, we are trying to investigate the mixing kinetics of UHPC, and the 3 impact factors will investigate it, such as mixing temperature, mixing volume, and mixing method. After that, we develop a mathematical model to describe the mixing kinetics of UHPC. And finally, we will apply the model to guide our large-scale UHPC production in the lab with a normal mixer. So Firstly, to quantitatively evaluate the mixing torque during the mixing process, the ICAR plus rheometer is used in this test. And the mixing, as shown in the figure in the bottom right, you can see the mixing torque is tested every 30 seconds after the water is added into the mixer. And the first step, we conduct the preliminary studies. We can see the dramatic mixing torque variation occurs in the stage 1. That's we can see the motor homogenization process. And the steel fiber, actually, the addition of steel fiber has negligible effect on the evolution of the mixing torque. So in this research, we mainly focus on the stage 1 to figure out what happened. Now here is a mixer design we selected in this research. And as I introduced before, 3 mixing variables will be investigated. First is the mixing temperature, second is the mixing volume. And for the mixing method, 2 types of mixing method will be investigated in this research. We call it the mono-batching and the multi-batching method. And we can see the mono-batching method refers we add all the dry raw materials and the water materials into the mixer at the same time. And we start the mixer to homogenize the UHPC. And for the multi-batching method, here we use the 2-batching method as an example. In the first round, we just add half of the water and superplasticizer and dry materials into the mixer and make sure it then mix it. Then we add another half of the dry materials and the liquid materials into the mixer. And the interval time between these 2 batches were also investigated. So let's see the effect of mixing temperature and the volume on the mixing torque. Before I introduce this slide, I will explain the label of the figure. The MY represent the M1 mixture, and the 1.5 represent the mixing volume is 1.5 liters. And the 10C represent the mixing temperature is 10 degrees. So from this picture, we can see that mixing torque is increased with the mixing volume and temperature, which is very clear. And the peak mixing torque is reached at 90 seconds. So after that, we conduct a regression analysis for the peak mixing torque. We can see the peak mixing torque linearly increase with the mixing temperature and the mixing volume. And in these 2 figures, the slope of the fitting line represent the increasing rate of the mixing torque. So we can clearly see that the peak mixing torque is more sensitive to the mixing volume compared with the mixing temperature. So next, let's see the effect of mixing method and time intervals on the evolution of the mixing torque during the mixing process. The same like before. Let me introduce the name of the label in this figure. The M1 also represent the M1 mixture, and the first 1.5, we can see here, first 1.5 represent the first 1.5 liters is added at 0 seconds, and the second 1.5 liters was added at 188 seconds. And the 20C represent mixing temperature is 20 degrees. So we can see as the interval time between the 2 sub-batches is sufficient in this research is over 90 seconds. The 2 peaks of the mixing torque are generated. And we can see compared with the mono-batching method, the 2-batching method, the peak mixing torque of the 2-batching method is significantly reduced. So after that, we want to know if there is any difference between the first sub-batch and the second sub-batch. From the results here, we can see actually the second sub-batch takes shorter time to reach the homogenization, and the peak mixing torque of the second sub-batch is pretty close to the first one. And the third conclusion is the same with before, when the interval time was 2 sub-batch is sufficient, and the mixing torque evaluation of the second batch will stabilize. You can see we conduct the 90 second and 180 second. So what is the reason the second sub-batch takes shorter time? So let's say for the mono-batch method, like we introduced before, due to the low water to bind ratio, the consolidation can happen, and consolidation and growth stage can happen only by the water squeezed from the inside of granulars. But for the multi-batch method, we can see actually the mixing process for the first sub-batch is the same, which will rely on the water squeezed from the inside of granulars. But for the second sub-batch, we can see the extra water from the homogenized of the first sub-batch can help wet the surface of the second sub-batch. That's why it takes shorter time for the second sub-batch to reach the homogenization. And also, it can reduce the mixing torque. So after we conduct so many results, we found a similar regularity. From the first figure, we can see the mixing torque generally just increase, decrease, and stabilized with the mixing time, which is very similar with the Gaussian distribution curves. And the mixing torque also increased with the mixing temperature and mixing volume. So we propose a model to try to describe the mixing kinetics of UHPC during the mixing process. So for the constant A, B, C, alpha, beta can be determined through the regression analysis through some lab scale tests, some small lab scale tests. So first, let's try to verify the monobatching model. So the regression analysis was conducted to determine the monobatching constant using the experiment data. So in the results, we can see the test results are in the solid lines and prediction results are in the dashed lines. So we can see actually the developed model can precisely predict the mixing torque evaluation at different volume and different times. And the second one, we're trying to develop the multi-batch mixing model. Actually, the multi-batching, the total mixing torque of the multi-batching is just the superposition of the mixing torques of the different sub-batches, right? So actually, we just need to get the constant for different sub-batches and do the superposition. Then we can conduct the model for the multi-batching. Then here we can see the same with the before. The test results are in the solid lines and prediction results are in the dashed lines. We can see the developed models can precisely predict the mixing torque for the first for the first sub-batch and second sub-batch. After we do the superposition, we can conduct the model for the multi-batching method. After we conduct that result, we are thinking if our model just apply for our mixture instead of other one. So we're trying to verify the model through the different UHPC mixtures. So based on that, 3 additional UHPC mixtures are proposed. For the mixture M2 and M3, we use a viscosity modified agent to just verify the viscosity of the mixture. And for the mixture M4, we totally revise, change the binder component. So we can see here is the fresh properties of the validation UHPC mixtures are in the below table. So then we conduct the results. Through the results, we can see, although the model constant for different type of UHPC mixtures are different, but the mixing kinetics models can still works well for different mixtures. You need to conduct some small batch test to do the regression analysis and to conduct the model. Then after that, we are thinking about another problem. If the model can apply for the different mixture designs. For example, we use the 2-batch method as an example in this research. So we're trying to validate it through the 3-batch method, which is to equally divide the total batch into the 3 sub-batches. So from the picture, we can see when the 3-batch method was applied, the peak mixing torque is further reduced compared with the black line, which is a monobatching, and the blue line, which is a 2-batch method. So which also represent the multi-batch method can efficiently reduce the peak mixing torque. And we can say as a interval time between the 3 sub-batches is sufficient. We can conduct the same conclusions. We can solve the 3 different peaks, and which is very similar. And here is the constant determination for the mixing method. We can see which is very similar with the different mixtures. We can see the model constant for different sub-batch are different, but still the mixing kinetics model works well for the three-batch method as well. And after that, we're trying to think if the multi-batch method can affect the key properties of UHPC, because the method is totally different. So we conduct the flash properties, mechanical properties, compressive strength in this research, and the heat flow, hydration heat flow, and the autogenous shrinkage test. We can see compared with the mono-batch method, actually the multi-batch method has negligible effect on the key properties. So after all this work is done, we are trying to apply the model to guide our large-scale mixing in the lab with some normal mixers, not the very high-tech mixers. So the first one, we determine the UHPC mixtures in our lab. This is the mixture we're trying to do the large mixing. The first step 2, we're trying to determine the model constant. Actually, I already showed the constant in the former slides, and we will have the constant for the mono batching, 2 batching, 3 batching as well. And then step 3, we need to calculate the peak mixing torque with different method. So in this step, we need to have the constant we have already conducted in the step 2, and we need to determine our target mixing volume and the mixing temperature. So in this project, we just do the 4 cubic feet, which is around 115 liters, and the mixing temperature is around 25 degrees in the lab, because it's just the lab test. And we can calculate the peak mixing torque for the different method, which is 1,600 for the mono batching, 905 Newton times meter for the 2 batching, and 675 for 3 batching Newton per times meter. Then step 4, we need to compare the peak mixing torque of the different mixing method with mixing capacity of the mixer. So usually the manufacturer of the mixer will provide us mixing power, or we can see the mixing capacity, which is horsepower or kilowatt. And they will also provide the rotation speed, which is RPM. Then we can calculate, in our lab, we calculate the limited mixing torque of the mixer is 990 Newton times meter. Then we can see, compare with the multi-batch method, 2 batch method, and 3 batch method. Although we can say the 2 batch method is pretty close to the limitation of the mixer, but to the safety concern, we select the 3 batch method in our research. Then let me show the results. We conducted 2 research. This is when we use a mono batch method. Let me repeat it again. It's stuck. So the materials was wasted. Then after that, we tried, let me back. Try the 3 batch method, the same volumes and mixture, it works well. And yeah, so let me do a brief conclusion for my presentation today. For the UHPC production, the mixing time, as the mixing time increases, the mixing torque will first increase, then decrease, and finally stabilize. And the mixing torque proportionally increase with the mixing temperature and the volume. And the second one is the multi-batch method that we propose can efficiently reduce the peak mixing torque for the large-scale UHPC production especially in the lab. And the third one, the accuracy, reliability, and the repeatability of the mixing kinetics model that we proposed is verified by different mixer design and different mixing method. And fourthly, is compared with the mono-batch method. The multi-batch method has negligible effect on the key properties. And all the tests was conducted in our lab, ACT lab. Our lab is in the riverside of the Hudson River, which is facing the midtown of the Manhattan. So welcome to visit our lab. Then we're gonna give the acknowledge to the National Science Foundation and New Jersey Department of Transportation. And we also would thank to the research associate and student in the RAIN group in Rutgers University. It's a collaboration project. And we also need to thank to the Mr. Surush and Dr. Li Bao for the valuable suggestion for the project. Yeah, thanks for the watching. Any questions?
Yeah, thank you so much. truly speaking, it's an wonderful work. Like most of the time, we end up with a damaged machine while we are mixing. So my question is, you mentioned about extra water for 2-batch mix. So did you added more water, or it is the second water? So
I understand the question. You mean this slide? Let me back to. You mean when, why for the second batch we have the extra water? Actually, that's not the extra water. Just I think you're asking about these slides. This one, right? The extra water from this one, actually we don't add the extra water because when we add the second sub batch, actually the first sub batch is already homogenized, right? We can regard the first sub batch as we can call it like the viscous water because it's already homogenized. It's not like the dry materials. So that part of the first sub batch can help with the dry materials from the second batch, which is just added into the mixture, right? So that's why it can reduce the mixing time, and also it will not further increase the mixing torque because they are already homogenized, right? Yeah.
There is also dry material when you are adding in the next batch, right?
I'm sorry.
On the second batch, when you are adding water, that there is also dry materials, right? So the water content should be for mono batching and multi batching or 2-batching, it should be same. So there should be some other reason that it take time, less time, right?
Before we conduct the research, right? Then we will totally divide them into the different sub batches. For example, first sub batch, we will divide the dry materials half and half, and the water and superplasticizer, we will also divide them to half and half. So we mix the first one, mix the second one, is totally independent. They will not affect each other. Yeah. Thank you for the question.
Thank you for the great presentation. So I want to ask, when you use the multi-batch mixing, is it possible to increase the mix volume? So you had the table in the beginning comparing the mix capacity and the allowable volume, I think. No, can you go to the beginning? You had the table comparing the mix capacity and the allowable volume. Yeah. So is it possible to produce a larger mix size at the same mixer when using multi-batches?
Right, but we have less power. Our mixer is an electronic engine, so which just have a 5 horsepower. This one is 11 horsepower. So but we also mix the 4 cubic feet, which is pretty close. But actually, you can see the mixing power of this type is twice of the mixer one. So I think we can get higher that mixing volume. Yeah, thank you.